We're going to talk about chapter 11 in this video, and we will have to split it up into two parts, mostly because there's a lot to say about groundwater. So starting out, we've got that the hydrosphere is all the water that's found on the earth. So it's in the soil, it's on the surface, it just seems to be everywhere. Most of the Earth's water is located in the oceans. I know that doesn't come as a surprise, 97.2%. But what may surprise some of you is that most of the fresh water on our planet is tied up in ice. It's in glaciers and other ice formations. And that's 2.15% again of this tiny amount of water that's available as fresh water. Remember, 97.2% of the Earth's water is salty. So a little bit of our total water and almost all of the fresh water are in the form of ice. Then we have groundwater. If your water comes from a well, you get it from groundwater. And then we have lakes. So there's a freshwater lake and a saltwater lake. You can see the percentages are about equally split on that. You can see some moisture is held in the soil, some is in the atmosphere. That would be the clouds and the air we breathe. And then this little teeny tiny number is found in our rivers. Why is that significant? Well, you and I in Hickory get our drinking water from the Catawba River. If you purchase water from the city of Hickory, it comes from the Catawba River. If you are using a private well, then you're getting groundwater. So drinking water is obtained from either surface supplies like rivers and lakes or groundwater. And again, the groundwater is if you have a well or you purchase water that comes from a well. There are a lot more wells in Catawba County than most people realize. So what determines how much of the water ends up in the ground? Well, it's a complicated issue. It's controlled by the climate. Does it rain a lot or a little? The population, the more people you have in an area, the less likely water is to soak into the ground. They have more houses, they have more parking lots and more malls, and all of that takes land surface out of the equation. So the more people you have, the less free surface to the earth you have for water to soak down in. The rock type makes a difference. Some kinds of rock allow water to soak down into the soil very easily. Some make it very, very difficult. The amount of vegetation can be a controlling factor as well. Sometimes in an area, if there's very little vegetation, the soil becomes very hard and compacted, and instead of the water soaking down into the ground, it rolls right off. So vegetation plays a role, plus roots for a plant will get down into the soil and open up little spaces that allow the water to percolate down. And then finally, land slope. If your land is flat, more water will soak in than if your land is tilted. If you're on a slope like the side of a mountain, water is going to roll off. So in general, about 15% of precipitation ends up as groundwater, but it just depends. It can be as little as 1% or as much as 20%. California withdraws more groundwater than any other state. There are a variety of reasons for this. There are a lot of people that live in California. California has a huge landmass. It is a really large state, but it also has a lot of agriculture. There are lots of crops that are grown in California, and that impacts the amount of water that the state uses. Let's look at our first graphic. This is from 2015. This data is updated every 5 years, but the 2020 data won't be available until 2021. So we're stuck with 2015 data. You will notice that the dark blue colors indicate that the most water is withdrawn. Notice this total withdrawals. So that's groundwater and surface water, ground and surface. You will see that California and Texas lead the way. California, I've already explained why it uses a lot of water. Texas is uh, physically a large state. It doesn't get a lot of rainfall, and it does have agriculture. Texas has cattle, certainly, but there is also cotton is grown in Texas, and there are other crops as well. In fact, it's noted for its citrus crop. So Texas uses a lot of water. California uses a lot of water. You will notice that in the next category, the 10,000 to 20,000 range, New York, North Carolina, Florida, Arkansas, Illinois, and then a scatter of other states are in that category. And then you can go down from there. So this is total withdrawals, that's surface and groundwater. If we look just at groundwater, you will see that again, Texas is the leader in the millions of gallons withdrawn from wells, and that North Carolina falls dramatically. Most of the water that we use in the state of North Carolina is surface water. We're very blessed to have a large system of rivers and lakes and streams, and so we don't depend on an aquifer on an underground supply of water in the ground. But you can see some states do. So let's look at some trends. The graphic is from the year 2000. I realize that's old. We'll compare it with some more recent data here in just a minute. But I want you to notice that in the graphic, irrigation takes the lion's share of the water. Most freshwater withdrawals, whether it's from surface or groundwater, are used for irrigation purposes. And back in the year 2000, that was 56,900 million gallons per day. You can see that the next closest category is the public water supply. So the water that you and I buy from the water company. And then it goes down from there. So irrigation is the big user of water. If we look at this, and now we compare our pie chart. Again, you can see it was 68% for irrigation in the year 2000. If we come down to numbers for 2015, you can see that irrigation still takes a hefty chunk of the pie. But if we did our numbers, irrigation drops to 36.7% of water withdrawals. So we've done a better job. And how is that possible? Do we grow fewer crops? No. What happens is that in previous years, irrigation was a farmer would have a device that would in essence be an enlarged garden sprinkler. It would throw the water into the air, and the other air particles of water would fall down and water the crops. But now we are a little more careful about that, because the old technique, a lot of water was evaporated. In the newer techniques, instead of throwing the water into the air, actually place it on the soil where it's needed, and in some instances, even on individual plants. They use soaker hoses that have little holes poked in them. They use drip irrigation where each little plant has a hose. There are a variety of techniques out there, but we really have gotten much better at irrigation. You will see in this 2015 graphic that thermoelectric power now uses an enormous amount of energy. Of water. I'm off on something else. It uses an enormous amount of water. So what is thermoelectric power? That is any electric power generation that involves the heating of water. So if you have a coal burning power plant, natural gas burning power plant, or a nuclear power plant, all three of those boil water to make steam to drive a turbine. And so in this instance, what we have are examples where that uses a lot of water. But the graphic is deceptive. It uses it in what we refer to as a pass-through process. What that means is the water comes in, it's used to generate the electricity, but it goes back to its source with minimal loss. Some of the water does evaporate and make steam clouds. If you've ever driven by a power plant in, excuse me, in North Carolina, you might have seen what looked like smoke coming out of smokestacks. That is actually steam coming out. And so you see a little water loss that way, but very little. So the graphic is misleading, I think. So let's look at trends in total water withdrawals by category over time. This graphic covers the years 1950 to 2015, so an enormously long period of time. You'll notice that the blue line, which is total withdrawals, had a peak in roughly 1980, and then it leveled off between 1980 and looks like about 2005, and now it's come down from 2005. So what happened is we didn't worry too much about conserving water in the 1950s to the 1980s. We used what we wanted. And then we became more aware that we might want to think about not being quite so wasteful. And then finally, in 2005, we started doing a little something about it in a significant way. Primarily, the way has been to have more efficient industrial processes. And in our homes, there are low flow shower heads, low flow toilets, more water efficient dishwashers and washing machines. We have had legislation put into place that encourages all of us to conserve water in some fashion. And so there's just been a concerted effort to do a better job. So total usage has dropped. Again, let's look at some of these categories. Irrigation is this turquoise one. So you can see it went up, 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 peaked in 1980, leveled off, and it's come down a little, but it has certainly not plummeted. Thermoelectric power, remember that's power plants that generate heat to boil water, to make steam, to drive a turbine. Started out small, peaked, leveled off, and again, we've come down some. And you see our public supply, so that's the water that you and I use in our homes, has pretty much been steady since the 1970s, 1980s. We've sort of leveled off. Well, let's look at trends in population and freshwater withdrawal. So let's compare it to the number of people. The hot pink line is the population. You can see that it goes up, up, up. We have not leveled off. There are still people being born and we live longer. So the trend goes up on population. You can again see that the total freshwater withdrawals peaked at about 1980, leveled off, and you'll see that since 2005, again, we have come down. And again, that's through a real effort to conserve water. So let's talk about some of the ways water gets into the aquifer, gets into the groundwater. Water soaks into the ground, and the amount of water that soaks in is dependent on the porosity and the permeability of the rock. So porosity is the amount of open space in the rock, and permeability is the interconnectedness of those open spaces. So the pores, the open spaces, the P-O-R-E, hold the water, and the permeability lets it flow. So certain types of rocks are more porous and more permeable than other types. If we look at our graphic, the low permeability would be things like shale or the metamorphic rocks, things of that nature, some of the igneous rocks. The high permeability, well, gravel and sand and a lot of the sedimentary rocks fall into this category. or things that are easily dissolved by water. So limestone is easily dissolved by water. Basalt tends to crack, and so that's why it falls into a high permeability. As I've said, sand and gravel has good porosity and good permeability. Lots of holes and they're interconnected. So let's talk a little about the water table. So with the water table, water soaks down into the ground, and when it gets as low as it's going to go and starts filling up every open space, we are in the saturated zone. The zone above that, where there is some water, but every open space is not full, is called the unsaturated zone. And then the water table is the line that separates the two. The water table is the line that separates the two. And it will fluctuate depending on climate and use. So here we've got a little graphic. You can see our little tree and a cloud with some rain. So the water soaks down, it moves through the unsaturated zone. We call that process infiltration. And it ends up in the saturated zone where, again, every open space is full of water. And here's our water table. If the rain stops, but we have our wells, then the water table may drop. If we have a really wet period, the water table may rise. So the water table is a fluid line. It comes and goes depending on climate and water usage. We look at this graphic, it shows you a little bit about the saturated and the unsaturated zones. The zone of aeration is the unsaturated zone. It's a place where there are open spaces, but again, they're not all full of water. Plant roots will work their way down into the soil and loosen it and provide open spaces for water to percolate down. Insects are a key feature in this. So worms and ants and things of that nature burrow down into the soil and make natural openings for water to pass through. So wells and lakes indicate the level of the water table. We will have a lab where we use lake levels. The lab looks at lake levels to tell the level of the water table. If you have a perched water table, what that means is it's tilted. Part of it is up high and part of it is down low. If the soil erodes and a part of the lower section of a perched water table is exposed to the surface, then what happens is that water will naturally percolate out of the ground and you will form a spring. You will form a spring. So it's just an area where water can come naturally to the surface. And it's because the aquifer, the water table, is at an angle. And gravity just feeds it up to that exposed area. We'll have a little picture that'll help us with this in a minute. So the movement of groundwater moves out both horizontally and vertically. It goes down, 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 and out, out, out. It goes from high to low, and then spreads out in the horizontal direction as well. As it moves through the soil, it carries dissolved minerals with it. Every time the water passes over soil and rocks, it dissolves a little bit of minerals with it. So salts and other things get carried down into it, which is why we're really concerned about keeping the soil clean. This is why there are rules concerning landfills and how you dispose of your garbage, and why we care about what goes into our rivers and lakes and streams. And it also flows downhill. Water collects in a low spot, and that's where you get a lake. So let's look at aquifers. So it's a body of saturated rock or sediment, and the water moves easily through it. So you can drill a well down into it and insert a pump and pump it up out of the ground and use it. Some whole communities rely on a well. So aquifers have areas of recharge and discharge. Discharge is where you take water out of the aquifer. Recharge is where you put it back in. Recharge would be in an area like a lake. Discharge would be a well. You've dug down into the aquifer and you're pumping water out. As long as recharge balances discharge, your aquifer is stable. You can have an artesian well. This one doesn't require a pump. What happens is an artesian well is dug below the area of recharge, and so gravity naturally forces the water out of the ground. So they do not require pumps. So let's look at our little diagram. So area of recharge would be up here. There's a little lake and the rain falls into the lake. Some of the water soaks into the ground. We've got resistant rock down below that keeps the water trapped. And where the topsoil erodes away down to the level of the aquifer, you have a spring. If we come down and we have an opening into the lower part of the aquifer, it can be an artesian well. Remember, it doesn't have a pump. Water comes to the ground naturally. You can see the difference between an artesian well and a spring is the size of the opening. A spring's opening is really large, an artesian well is narrow, but they are both downhill from recharge. Let's look at some of the ways groundwater can be contaminated. So you can contaminate it by the improper disposal of waste. You don't want to throw anything onto the soil or down a storm drain that you don't want to have end up in your drinking water. Or for that matter, you don't want to flush it down your toilet either if you don't want it to end up in your drinking water. It used to be very common for people to flush unused prescriptions down the toilet. Now that is not recommended because the water in your home will eventually end up as part of your drinking water supply. It is obviously treated before you get it, but still the wastewater treatment and the water treatment facilities only look for certain things, and there are thousands and thousands of different materials that could end up in our drinking water. So we'll have a little separate exercise on the proper way to dispose of drugs, but you don't want to just, and for those of you who don't know, a storm drain is that area in the, suppose you're in a city with a sidewalk, if it's elevated above the roadway, sometimes there'll be a little cut opening in it, and when down at road level, and when it rains, water will go down into that little opening. The little opening is a storm drain, and the water that enters it goes directly to lakes and rivers. And that's where our drinking water comes from. We get our drinking water directly from Lake Hickory, which is part of the Catawba River. In Hickory, it's right there, the water plant for our drinking water is right there on 321 at the bridge where it crosses between Catawba County and Caldwell County at the Arby's. So right there when you go over, if you were heading north to Boone. So we don't want to throw away things without being thoughtful. Pesticides, herbicides, and fertilizers. So pesticides kill insects, herbicides kill weeds, fertilizers make things grow. Used in the right amount at the right times, these are very beneficial. Used too much at the wrong time, they can end up in our rivers and lakes and streams. I'm sorry about the interruption. Too much, they can end up in our rivers and lakes and streams and do bad things. Too much fertilizer in particular is responsible for the algal blooms that you see in some waterways near places where there's a lot of agriculture. So liquid and solid waste from septic tanks and sewage plants can also be an issue. If your septic tank overflows, it can contaminate the groundwater. There are actually rules about septic tanks, where they can be placed, and how close you can then have a well to where a septic tank is located, or in particular where a septic tank can be compared to a stream or a lake. Sewage plants, well, they're not perfect. Every once in a while there's a leak and bad things happen. Acid mine drainage is an issue as well. So in mines, they, as long as they're open and running, water's pumped out of them and it's not an issue. But when a mine is closed up, there's an open space where water can seep down in, and it can carry natural materials that you wouldn't want in your drinking water out of the ground and into the water supply. And then there's just normally things that are in the soil that we probably wouldn't want to have in our drinking water. So arsenic and selenium and mercury, these are all considered unacceptable materials in the water supply. And normally it's treated fairly well, and we really have a very safe water supply, but we have to do our part. So the little graphic just shows you all the different ways. It sort of consolidates all the different ways that material can get down into the water supply. So agricultural runoff, if you're a pig farmer, the waste material is sometimes held in what's called a lagoon. Until it can be treated and spread on fields. And sometimes, besides smelling bad, it can, if it rains a lot, that can spread out over the soil and sometimes pollute the groundwater or your neighbor's water supply. Maybe there's a stream or a freshwater pond. All kinds of other things. Caves, abandoned storage tanks, industrial applications, urban runoff, everything that's on the ground or on the highways eventually ends up in the water supply. There are certainly municipal issues with treatment plants, again, that have unexpected leaks. And with landfills, a landfill is where your trash goes, and there's certainly rules and regulations about what can go into the landfill. It's lined, but again, problems can occur. So we just want to follow the rules and regulations. Saltwater intrusion is when you have saltwater permanently contaminating fresh groundwater because over pumping of the aquifer. So in our little graphic, we have a well going down into the water supply, the fresh water, and it's near the ocean. So what will happen is that when you pump water out, you get what's called a cone of depression, that locally that water drops. And if it drops below the level of the ocean, the water likes to seek a uniform level. And so if you start dropping, fresh water will float on top of salt water. But if you have it drop below the salt water, then salt water will seep in and pollute the groundwater. And once it does that, you can't clean it up. Once it's polluted by salt water, it stays polluted. So again, it's a result of over pumping of the aquifer. So if you live in a coastal area and they say we're in a drought, don't wash your car, you need to follow the rules and regulations because it's to prevent saltwater intrusion. So you need to balance recharge with discharge, adding water with taking it out. If you remove more water from the groundwater, from the aquifer, than soaks back into it, you run the risk of subsidence. That's where the land sinks because the water's not supporting it anymore. And you can see from this graphic that there are certain places in the country, these blue areas, where subsidence is more of a problem than other locations. The United States is not the only place that suffers from this. This is a map of the UK, so England, Scotland, and Wales. And again, the green is an area where it's fine. If it's yellow or orange or red, subsidence is an issue. And again, it's because overpumping the aquifer and then salt water seeps in. So some of the effects of groundwater action, you can make all kinds of really cool things with groundwater caves and sinkholes and stalagmites and stalactites. Those are all covered in the lab. I will remind you right now that the G in stalagmites helps you remember that it grows up from the ground, and the C in stalactites helps you remember that it grows down from the ceiling. So today we're going to look at two examples, petrified wood and geodes. So with petrified wood, it's a multi-step process. You have a tree and it dies and it falls over and it gets covered by water that has a high mineral content. And then, so the water all soaks into the little cells in the wood. And then the climate changes and the water evaporates. And so the water leaves, but the minerals that were in the water stay behind, and they turn to stone, to rock, usually some form of quartz, since quartz will dissolve in water over a very long period of time. And the result is petrified wood. This is a log from the petrified forest. If you're on your way to the Grand Canyon from the East Coast, it's on your way. You can stop in. Another thing that can be formed by groundwater are geodes. So with geodes, you have a rock of some shape. It doesn't have to be round, and it has cracks in it so that water will get into those cracks, and somehow a hole is created. Now the hole may be there in the rock in the first place. It may be because that's the kind of rock that has a cavity, but a hole is created, and then water, again with a high mineral content, seeps in, fills up that hole. Over time the water evaporates, but the minerals get left behind and they form crystals. So the outside of a geode just looks like a round stone of some sort. I've always thought they look like old cannonballs. They can be small, like half the size of your fist, or they can be enormous. And again, they don't have to be round. So this is what a pretty geode looks like when you cut it open. The rim is microcrystalline quartz. So the rim is solid quartz where the crystals are so small you can't even hardly tell they're crystals. And the interior of the cavity has larger crystals in it. This one happens to be full of amethyst. They're not all purple when you cut a geode open. Sometimes they're smoky quartz, sometimes it's just clear quartz. It just depends on the little bits of additional minerals that are, or elements that are in the quartz water when it soaks in, and it gives it a different color. And they're not all hollow on the inside. Some, if they water evaporates over a very long period of time, the crystals will be large. If it happens really quickly, the crystals will be small. And in some instances, there are no crystals at all. It's actually solid in the middle. So the rim is called, again, I mentioned it was microcrystalline quartz, which is another name for agate. Let's look at hot underground water. Primarily, we're talking about geysers and hot springs and the differences between the two, geysers and hot springs. So let's look down at our graphic. So we have a heat source, probably the magma in the earth. It heats up the water in the ground. If the water congregates in a small enough area, it will turn into steam, it boils. If there's a straight connection between that boiling water and the surface, the water will just continually, because hot materials move up, it'll continually rise up due to convection, push the water up and out, and you'll have a hot spring. These have a high mineral content, so you'll find all kinds of interesting rock formations on the edges. And it's continually fed by water heated from deep underground. If that water goes up, but instead of having a straight shot, enters a larger area where it can pool and collect, it acts a lot like a pot with a lid on it. And so steam builds up, and then only when there's enough internal pressure will it then force the water up and out, and that's when you have a geyser. So straight shot down, it's a hot spring, has to have a staging area for the pressure to build up, that's a geyser. Hot springs are continuous, geysers are intermittent. Hot springs have beautiful and interesting rock formations associated with them. One of the most famous is Mammoth Hot Springs in Yellowstone National Park. This is just one photograph. I'm sure you could Google Mammoth Hot Springs and see lots of gorgeous ones. So in what these places that look like little stepping stones, they're little pools of water. I apologize that I didn't get a photograph of that up here. I'll have to work on that. You see hot springs in places where you've got volcanic activity, either current or in the past. And I've said that geysers, again, are intermittent or periodic. So the water collects in that reservoir, builds up pressure, and then shoots out. Probably the most famous is Old Faithful in Yellowstone National Park. It is periodic, and there are signs all around the park that tell you when it's next going to erupt. It really is very interesting. They have little benches placed around it for you to come and sit and wait and watch. And it's a great park if you've never been. Hopefully you'll get to go sometime. Again, Yellowstone National Park. But there are lots of other places with geysers. Let's talk briefly about geothermal energy. So that's any energy that comes from naturally found hot water. We use it to heat directly or create electricity. So how would we use it to create electricity? Well, it's pretty straightforward. The hot water comes up. You use it to create steam. The steam drives a turbine, just like in a regular coal-fired power plant or even a nuclear power plant. Generates electricity. That hot water is then cooled off, and then it's pumped back in the ground. Remember, I told you that power generation doesn't consume the water it uses. It's a pass-through process. The water comes up, it's used for its purpose, and it's sent back down. So Mexico, New Zealand, Japan, Iceland, all of these places use geothermal energy. The United States does as well. And in fact, the largest geothermal field used for power generation is called the Geysers, and it is in California. This photograph is not of the geysers. This photograph comes actually from Iceland. What I loved about it is that you've got these people in this hot spring. You can see the steam coming up, and then you have a power plant back here, more steam coming out. Iceland is noted for its hot springs. Again, Iceland sits on tectonic plate boundaries, and you are able to extract that energy. And that stops our lecture.